We've got the test solutions here for the data analysis test, or the chapter 3 to 5 test. So let's work them through. Alright, question 1 starts you off fairly easily. The value of Pearson's correlation coefficient, so that's the R value, okay, what we're looking for this scatter plot. Now, what we're going to get is a fairly good R value here, and it's positive as well, okay. So that rules out this one here. Whoops, I've got the rubber on. Yeah, that rules out this one here and this one here, because they're both negative. Alright, the correlation can't be 0, okay, and 0.3 is just too low, okay, so that's too low. So a definite answer is this one here. Alright, student scores on their English and Maths exams were found to be linearly related with an R value of 0.8782. So when we're talking about variation in English scores, why is it always going back to the rubber? Variation in English scores, that could be explained by variation in math scores. We're talking about R squared, okay? So when we're talking about R squared, what we've got to do is square this R value, okay? Now, just experience tells me that when I square it, I'm going to get a number a little bit smaller than that. So I'm going to get 0.77, something like that. So these are the only two that could be correct. This one is it converted to a percentage. This one here, whilst you might think it might be correct, that's actually 0.7712 divided by 100. Because it's a percentage, okay, which is just far too small, okay. Now the mathematics of it, just go over here and we'll work it out. I've got 0.8782, and we're just going to square that value, and then we get the 0.77, and then we convert that to a percentage by multiplying the answer by 100. So there's the answer. Alright, this one here, students always struggle with it. This question, it always sort of seems fairly simplistic, but yeah, it's a tough question, this one. So which graphical display would be most appropriate for displaying the relationship in salary? So we've got a numerical, and age group, okay, which is categorical, okay. So scatter plots out, that's numerical v numerical, okay. Now what we're doing is back to back looks at two pieces of data being compared. Right, here we've got lots of different data, here we've got lots of different categories being compared, back to back stem plots out. Now the histogram, all that would do is look at the number of people, say, in each age group, okay. We're looking for a relationship between salary and this, so no. Okay, I've got two variables here. Alright, segmented bar chart. Well, how could we show it? I mean, we've got a categorical variable, which, you know, may be appropriate to put in a segmented bar chart, but what are we segmenting it on? Okay, so no, can't happen. Therefore, parallel box plots is the only way, or the most appropriate way of demonstrating this. So the relationship between salary and age group, and the way I imagine it is, you know, we've got the age group 20 to 29 here, we've got the box plot here, alright, and then we've got the age group up above it, 30 to 39, and we've got a box plot here. And oh, look at the medians, you know, it's increasing for this age group or something like that, okay. So what you would do is put all of them in parallel and compare. Alright, down here we've got the data here that's clearly got some sort of a relationship, but it's just not a linear one. So when we transform it, what we do is we just look up the circular transformations and find that particular one. You'd find that it was an x squared and a y squared that would be appropriate. Options B and C would be an appropriate way to linearize it. Okay, so what we've got here is a value of the coefficient of determination given for this particular graph here. Okay, they've given us the coefficient of determination, C of D. Alright, so what we're going to do is now we want to work out Pearson's correlation coefficient. So this is really careful, be really careful, this question comes up all the time. So most of you will know, oh, what you do is you square root, you do the opposite to get the R squared value. From R, you square root the value. Alright, and that gives you 0.84. Okay, now many of you will be tempted to go for that, okay, that number there, but that's wrong. So once you get your correlation coefficient, I want you to go and have a look at the graph, and you'll look that this has a negative relationship. Okay, as the age increases, the sleeping time goes down. Okay, so it's the negative 0.84 there. So really common question, that one. Alright, next question. The y-intercept of the regression line predicts that. Okay, so what we're going to do is have a look at this graph again and have a look at so let's have a look at the y-intercept, and it appears to be there. Okay, so it appears to be roughly 13.5. So let's go down, have a look. Oof, this is looking tempting, this one here. Okay, but before you answer this question, I want to make sure that you actually have a look and see where the origin is. And have a look at this, girls. Alright, so what we've got is a broken scale here. Okay, this graph starts at 3. That means 2 would be over here, 1 would be over here, and 0 would be here. Okay, so what happens actually is this graph would continue up along this line here. Okay, and so actually I know that the y-intercept will be more than 13.5. Okay, because the y-intercept occurs when x is 0. Okay, so what I need to look at, let's just see if there's any other answers here. When a child is 0 years old, they're predicted to sleep for, but this is looking better. Alright, so that's our answer there. Okay, so with the actual x, when x is equal to 0, it's going to be much higher than, well, not much higher, but a little bit higher than the 13.5. So also really common VCAR question, that one. So just be careful, make sure you look and check whether that is the origin, so that you can pick the y-intercept. If it's not the origin, you need to, you need to keep going, or you need to sort of consider the fact that it, could be, it will be some other value. All right. So what we're doing is we've got a possible residuals plot for this. All right, and there's a couple of different methods of doing this. We can go and have a look at the pattern. So we've got up, down, up, up. So let's have a look and see whether we can rule out any. So you can see here straight away that this one here is out, okay? Because the pattern we had was up, down, up, up. This is up, 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 down, up, up. So this has got some potential. And up, down, up, up. This has got some potential as well. Okay. So what I do is, so that's gone, because that's up, down, that's down, up, down, down. So that's no good. So we're down to 2 options. Alright, let's have a look at the point of difference between the 2 of them. Alright, so they differ on this residual and this residual. Okay, these ones here has a much lower residual. The residual is -1 on that one, and this is -0.5. So let's go back and have a look at the 3rd point from the right. So we're going to go back 3 points and check what the residual would be. So here's the 1st point, 2nd point, it's this one that we're looking at. And let's have a look. Okay, well clearly the value of the residual is not 1. If it was 1, the point would be down there, because that would be one whole space between 10 and 11. Okay, so it's going to be 0.5. So I think we've found a winner. It's this one. Okay, because this has a residual on this one of 0.5, not 1. Okay, the 1 residual is too big. Okay, what we've got here is waist measurements and weight of 12 men. Okay, relationship there, or that's the regression line. And using the variables waist and weight, the equation would be written as. So let's have a look. Based on this equation here, the y value is going to be this, the weight. and we get given the waste. Okay. Now, how did I know? Well, using this data, the equation of least squares regression line that then enables weight to be predicted from waste measurement. So what we're saying is, give me a waste measurement, and I'm going to try to predict weight. Okay, that means that's the RV, that's the EV, and in an equation like this, it's the response variable equals the 1.11 multiplied by the explanatory variable, take away 20. Okay. So then, what is the correct answer? It's going to be weight equals negative 20 plus, so it's D. Okay. Alright, this one here, question 9, was poorly done. When the equation is used to predict the weight of a man with waist measurement of 80 centimeters, the residual value is closest to. Okay. Now, let's have a look and find the actual. Okay. So what we're going to do first of all is find out the actual data point. So we were predicting the man with a waist measurement of 80 centimeters. So let's find him in the data. Here he is here. Okay. So the actual was 80 and his weight was 67. This is the actual. Now let's do predicted. Alright, so what we're going to do is 80, comma. Now how do we get the predicted? Easy, we just use the formula. Okay, so we can use it from the correct answer here, or we can just go back up to the original, which is here. So that's 1.11 multiplied by the given value, which was 80 plus, subtract 20. Whoops. And it says 68.8. So let's write that down. Okay, so you might have to dig up the formula on residuals, okay, but what I know is the prediction here is higher than the actual. Okay, so what that's going to mean is that the residual is going to be negative. Okay, so that could be my only answer, that could be my only answer. Looking at the difference between the two, okay, they differ by 1.8, okay, not by 11. So this could be the only correct answer, but you could run it through the residuals formula. So the residual is the actual take predicted, which will be 67 take away 68.8. That's going to be negative 1.8, which is approximately negative 2. Okay. Alright, in a study involving Year 12 students, the correlation between the number of late hours spent studying and concentration levels was found to be that. It can be concluded from this information that, alright, let's see, less late night hours spent studying causes better concentration levels. Okay, less late night hours spent studying causes better concentration levels. Well, I don't know, maybe. Okay, let's have a look at the graph. So what we've got, a correlation between the number of late night hours spent studying and concentration levels. Okay, so what we've got here is hours studying and concentration levels. Okay, and what they're saying, it's negatively, we've got a negative relationship here. So less late night hours spent studying causes better concentration levels. Hang on. Okay, so back at it. So yeah, basically it seems to be suggesting, or this graph seems to be suggesting, that the more late night hours you spend studying, the lower the concentration. Okay, and really the only one that really reflects this is D. Okay, there is some association, alright, it's not a great R value, between increased late night hours spent studying and decreased concentration levels. Okay. Alright, so this one here, which of the following statements is a correct comparison of the data? Okay, So what I'm going to do is just go to the correct answer on this one, which was D, okay, because this video is starting to become quite long, okay. The minimum number of bounces produced by the golf ball was more than the maximum number of bounces produced by the rubber ball. So let's just find out why this is true. The golf ball is here, okay, and what we're looking for is minimum number of bounces. That's the golf ball's min. And the maximum number of bounces produced by the rubber ball, there's the max, okay. So that's the only one that is correct. The rest of them are all false. Upper fence of the table tennis data is closest to. Let's go to table tennis. Alright, so it looks like the Q3 is, let's go with 41 and a Q1 of say 36. Okay, so we're going to run the fence test on that and just see what it says. Okay, so the upper fence is calculated by doing Q3 plus 1.5 times the interquartile range. So the Q3 is 41 plus 1.5 times the IQR. Now that's 5. 1.5 times 5 is 7.5. 41 plus no, I just did that. It's 41 plus 7.5. That is 41, so that will be 48.5. Okay, so let's have a look. The upper fence of the table tennis data is closest to, definitely there. Alright. Lengths and diameters of jellyfish, of a sample of jellyfish selected from a location recorded and displayed in a scatter plot. So what we've got is a least squares regression line, correlation coefficient. It can be concluded that. So again, really common VCAR question here. What we notice is that as these values increase, these values increase. So we're looking for increases in the explanatory variable of 1. Okay, so let's have a look. 1 milli increase in length, that's out. 1 millimeter increase in diameter, that's a possibility, and that's a possibility. So we're looking at as these, or as the explanatory variable increases by 1, what effect does it have on these y values, or what value are they going up by? And that's the gradient over here. That's the gradient, 0.87. So as it increases by 1, the lengths go up by 0.87. Answer's D. Alright, this one was not done particularly well, okay, and this question comes up probably once every, I don't know, 3 to 4 years. Alright, so what we've got here is Mr. Mahmood. He's done some dabbling with predicting his psych scores based on further maths results. Okay, so what we're going to do is use this particular formula. Okay, so you need to have this formula on standby. Where is it? It's this one here. Okay, so look up your notes and you'll find this particular formula here. And what we can do is, given the means and standard deviations of the x and y values, we can just push it into this formula here and calculate what the regression line will be. Okay, so let's do it. So what we're going to do is use this. We're going to multiply, to find the b value, or the gradient, what we're going to do is multiply the Pearson's correlation coefficient by the standard deviation of the y values, divided by the standard deviation of the x values. Okay, so I've got to go back to that. So I've got my Pearson's value, which is 0.82. I'm going to multiply that by the standard deviation of the y values. Ooh, now which one's the y values? Well, that's the response variable, the psych test scores. So it's 8.71. And then we're going to divide that by the standard deviation of the x values, which is obviously the further maths. Okay, so this will give us the gradient of the data, which is 0.73. And really, what we can do is have a look. We've got only that one and that one that can be a possibility. Now we've got to push on and now use this b value to calculate the y-intercept. Okay, so let's go back to the formula and have a look at that. I don't actually remember the formula all that well. So to calculate the a value, what we're going to do is take the mean of the y values and subtract them from the gradient multiplied by the mean of the x values. Alright, so let's do that. We've got the mean of the y values, which is 32, subtracted from the answer, because that's the b value, multiplied by, you just retype that if you want, but I just like using a and s, multiplied by the mean of the x values, that was 30.18, 10 points there. Okay, so closest to is the thing, so that's our answer, B. Alright, it's nearly there, and you can see that, you know, these multiple choice questions certainly take some time. Alright, so we've got this data here, and what we're going to do is a transformation. We're going to do the reciprocal y transformation. Okay, so we're going to type in the data. So I'm going to go Control Doc and add a lists and spreadsheet. I'm going to call this x variable and y variable, and we'll go 1, 2, 3, 4, 5, 6, 7, 8, and we've got 2, 3, 5, 6, 7, 11, 39, and 47. Alright, so what we're going to do is the reciprocal y. So remember, your headings might be a bit different depending on who teaches you and what they like you to do. So I'm going to call this reciprocal of the y variable. That equals 1 over all these y values. So 1 over all of yv. Alright, let's get an approximation for that. So I'm going to change my doc settings. Alright, get that off float 6 and drop it into float. And calculation mode, let's get an approximate. Okay. Alright, now let's run some statistics on it. So menu, menu 4, 1, and 3 for linear regression. Let's grab the standard x variable versus the reciprocal y value and check it out. So it's saying it's got a gradient of negative 0.6. Let's see if that gets us a winner straight away. And a b value of 0. Oh shit, none of them are right. Alright, we're back on here. Yeah, I don't know why I wasn't seeing this, but the answer is C. Okay, so we've got a gradient of negative 0.6. There's that. Y-intercept of 0.46. There it is there. So our answer is C. Alright, so that's the multiple choice. Let's go on a short answer. So part of the science experiment, Mr. May is investigating the level of carbon monoxide changes based on the volume of traffic. Alright, so this one here, what you had to do was construct the scatter plot, add the missing points. Should be no dramas there. Okay, so just look up 11 and 200. Okay, so there's 200 and there's 11, so you should have 1 point there. We've got 14 or 260 and 14. There it is there. We've got 10 and 150. And we've got 300 and we've got 18. Okay, so there's some easy marks there. Alright, we've got this equation here, and what they want us to do is draw that regression line. So basically choose a couple of points. Now something that's a bit of a giveaway here is they've given us the y-intercept 0.11. We should use that. Okay, that's very close to 0, so you know that it roughly goes through there. So let's just get an upper end point. Okay, so let's sub in 300 into this equation and see what happens. So we're going to go back to our calculator. We're going to go 0.11 plus 0.056 multiplied by the traffic volume. What did I say I was going to use? Let's use 300, 16.91. Okay, so let's plot that point on here. So 315, 16.91, almost 17. And so basically what you need to do is grab a ruler. I can't do this very well with a stylus, but you grab a ruler. Ugh, that is the worst regression line I've ever seen. But that's what you do, is connect up those two dots that you just put on there, and that's your regression line. Okay, you could choose another point from 50, 350, anywhere along there, but for accuracy, if you're given the y-intercept and an origin of 0, I would plot the y-intercept. Alright, Pearson product moment correlation coefficient is that. What does it suggest about the relationship? A lot of you went on to talk about the r-squared value, not asked about that. So what does the Pearson suggest? It suggests that we've got strong positive, and because we saw the data already, we can say linear relationship. Okay, now what they predicted is when the volume of cars hits 400, the carbon monoxide level will be 22.51. And what you've got to do is state whether that prediction is reliable. Okay, now a lot of you said it was, because what you did was you went over to your calculator and subbed it in. 22, oh goodness me, it must be reliable, but have a look. Alright, your data range here for traffic volume sits between 300 and the lowest value is here. Okay, now 400 would be somewhere down here. Now notice that there's no data here to suggest that this pattern keeps going. Okay, so this is actually an unreliable prediction. Okay, and so what you needed to articulate was something like that this is unreliable, and words to the effect of outside, I'm just going to summarize it here, the data range, and this is called extrapolation. Alright, so yeah, it's an unreliable prediction. I mean, it is the correct prediction for our regression line, but there's no evidence to suggest that the pattern keeps going. Alright, so the following is the residual plot for the least squares. It's missing a point marking the residual when the volume of cars is 190. We've got to get the actual. Okay, so it's 190, comma. So you have a look up here. Okay, at the data. There's 190 there. Okay, 190 and 10. So let's write that down. That's the actual. Okay, now we're going to get the predicted. Let's go back over to the calculator. Alright, our prediction model's still in there from the last question, so we're just going to multiply it by 190. Okay, so it's 190, and this is predicting 10.75. So that's the predicted. Okay, now to calculate residuals, remember it's actual subtract predicted. So we're going to do 10, take away 10, take away 10.75, says the residual is going to be negative 0.75. So we go down to our residual plot down here, 190, there's negative 1, there's negative 8, so it's a little bit less than that. It's around about there. That's where the residual is. Alright, does the residual plot support the contention? Well, it's a pretty random scatter, so yes. Random scatter suggests that the data is linear. Alright, now last question. Got a number of men and women surveyed on whether they believe marijuana should be legalized. 62 men were surveyed and 41 were against. Okay, so let's pop that data straight into this frequency table here. So we've got against is 41. The total males surveyed was 62. That means that it would be 41 take away 51, 61, 21. Now females was 71, so 43 were against. 71, so the difference there is 21, 28. Okay, state for each the variables attitude and gender represent categorical or numerical. Well, your attitude is either you're for or against it. You're in a category. You're in the for category or the against category. Same with gender. Gender, you're either a male or a female when you're surveyed. Okay, so both were categorical. Alright, the explanatory and the response. Okay, what we're looking for is, as the sex of the gender of the individual changes, we're looking at their attitude. Okay, so gender is the EV because that explains the attitude. Okay, so attitude is therefore the response variable. Alright, so we've filled in this table and a little bit preemptively because it wants us to do a percentage one. So what I would do is convert all of these to percentages. So that's 21 over 62 to the nearest whole number. I worked this out earlier, but you can do it again on the calculator. What you would have got is 34, you would have got 66% on this one, and you would have got 39% over here, and you would have got 61% over here, both of these columns totaling to 100%. So you needed to just work those ones out on the calculator. Alright, so again, this question is going to be a little bit hard to plot on the stylus or using my stylus here. But what we've got here is the male and the female bar that we're going to use. Alright, let's plot the once it percentaged. Okay, so let's plot the fours in males first of all. That's 34%. So here's 30, 35. It's going to be slightly lower. Alright, so you're going to rule this with a straight edge, but that's just I can't do that on this thing. Alright, so that's 34%. Then obviously the leftover is going to be, oh, that is the world's worst bar there. Alright, so 34, and what we've got there is 66%. Alright, females, what we're going to do is plot the 39. So it's just below 40. And the leftover, which was 61%. Alright, so the very last question. Does the bar chart lead to the conclusion that gender greatly influences the attitude to legalization? Well, it certainly doesn't. Okay, so no. Gender is not related to the legalization of. Alright, so why not? Okay, there is very little difference in males for or against. You could use legalization, which was, we're going to quote the percentage, 34% compared to females, which was 39%. Okay, that's it.